So in this session on signals and systems, we are going to study how to write a MATLAB program for calculating convolution. So far, we have seen how to analytically solve the convolution problem. Now we shall see how to numerically solve it by writing a MATLAB program. So let us start. So what we are going to do is to use a function called as a convolution function in MATLAB. And its syntax is like this: y equal to conv xh, where x and h are two signals whose convolution is to be found. Now it's important to note that MATLAB basically calculates discrete convolution, and this is the sum of products. Understand this. The analytic techniques that we have studied so far were applicable to continuous time signals. But the MATLAB actually calculates the convolution as a discrete convolution. So let us see the difference. So it calculates it like this. Now discrete convolution itself we will separately study in more detail later on. But right now understand that it is calculating simply the sum of the products and not the integral itself. Whereas right now what we are trying to do is to simulate the calculation of convolution for continuous time signals. So let us see how to adjust this convolution for that application. So what we really want is to do this integration. That is, you multiply these two signals, one signal as it is, the others inverted and delayed, and then integrate. Whereas the function in the MATLAB, what it returns is the sum of the products. That is what it returns. It does not directly return the integral. So we have to find basically a way of calculating the integral numerically when the samples are known. So first we will study that technique, and through that technique we will understand how to calculate the integral numerically, and then we shall see how we can apply the result of that to the calculation of this integral using this result. Okay. So let us start. Integration of continuous time signals in MATLAB. Obviously it's going to be approximate because essentially it's a numerical calculation. But let's see. So suppose you have a function xt is equal to 2t. So this is a straight line passing through the origin. So at t equal to 0, this is 0. At t equal to 2, it reaches 4, and it is a straight line. So analytically, we all know how to calculate the area. That is simply half the base into height. So that can be calculated. As I have said, analytically we know that area is 0.5 base into height, that is equal to 4 in this case, because base you can see is 2 units, so this is 1, and the height is 4. So 1 into 4 is equal to 4. So this is the analytic result. Now we want to do this numerically. So what do? So we sample the signal with certain sampling time. Smaller the sampling time, better will be the result. Understand that when we do the numerical calculation, it will always be approximate to some extent. It may not be exactly equal to 4. And the error that you get will depend on how small a sampling time you choose. The smaller the sampling time you choose, lesser will be the error. Okay. So to calculate numerically, we first sample the signal, say with Ts equal to 0.1 second. Now 0.1 second of course is not too small. The reason I have selected this is because then you can see the samples clearly and the technique can be explained easily visually. So that is the reason I have taken. In actual practice, this could be smaller than this. For example, it could be 0.01, 0.001 and so on. But then it will be difficult to explain the technique. So just now I am taking Ts equal to 0.1 second. All right. So if you take Ts equal to 0.1 second and then generate these samples. So at 0 it is 0, at 0.1 it has this value, 0.2 it has this value, and so on. So this is how various samples are taken. Then what do? Then each sample you assume that it is constant till the next sample comes. This will form a rectangle. Then take the next sample, assume it is constant till the next sample comes. That will also form a rectangle. and so on. And then what you can do, you can calculate the area of each rectangle and then sum all the areas. That is what you can do. So let me first show you the rectangles that are formed. So this is one rectangle, you can find its area. So x1 multiplied by ts. If this height is x1, that will be multiplied by ts to calculate this area. If this is x2, that will be multiplied by ts to calculate this area. So the total area can be calculated like this, approximately x1 into ts plus x2 into ts plus x3 into ts, etc. Now you can see that ts is common here. So you can simply write x1 plus x2 plus x3, etc. up to ts. So then what you can do, once you have taken all the samples, you can take sum of all the samples and then multiply this sum with ts. So this is the result that we are going to use in order to calculate the convolution for the time domain, because there sum of each samples for any value of n is known. Let me show that to you. Convolution function in MATLAB provides results for discrete. So it gives samples of sum of products. That formula we have already seen. So to get the value for integration for continuous time signals, we multiply by ts. Just now we have seen that sum of all the samples will have to be multiplied by ts in order to get the total area. Of course, it will be approximate. So for every value of n, all the samples are given by the convolution function. If you multiply them, the sum of the products is given by the convolution function, and if you multiply by ts, you can calculate the area. Okay. So therefore, all you have to do is use this convolution function and multiply it by ts. That is what you have to do. All right. So let us now take a concrete example and then develop the program for that. So suppose the two signals which are given to us are ht and xt, and ht lasts from -2 to +2, and you can see ht is simply linearly related to time, and in fact it has got a slope of unity. This is 0. From here you reach at 2 seconds, you reach the amplitude of 2. That means amplitude divided by base, that is equal to unity. In other words, the expression for ht between -2 and +2 is t itself. It is just a expression for the straight line with a unit slope. What about xt? It is a rectangular pulse lasting from -1 second to +1 second. Now, although our signals are really defined like this, that is ht is a straight line from -2 to +2, and xt is a rectangular pulse from -1 to +1. But it is convenient to plot for the same time vector both the signals. That is, in this case, we take a time vector which is a little more than this. So although this spans -2 to +2, we take from -3 to +3, and the same time vector we also utilize for xt. And the reason for this is that when you utilize the same time vector, you can see the relative positions very clearly. The zeros get aligned here, this -1 gets aligned. For example, if I had plotted xt from -1 to +1, then it might have started from here and all the way up to here. So then the relative positions you cannot very clearly see. For that reason, we will generate one time vector from -3 to +3 and use the same time vector for generating ht as well as xt. All right. So let us first of all see the program segment for generating ht. So this -3 to +3 is the entire time interval. This we can split into three segments, one from -3 to -2, then -2 to +2, and 2 to 3, three segments. In the first segment, you got all zeros. In the second segment, this is linearly related to time. And in the third segment, again, all of them are zeros. So let us write the program for this. So first we generate our time vector from -3. Now I have used a sampling time of 0.01 seconds. So -3, 0.01, 3. So this entire time vector is generated. From that, now you first generate the t1 time vector here. So it starts from -3, same sampling time, that is 0.01. But now instead of ending exactly at -2, it ends one sample time earlier. The reason is, from the next sample we want to generate this. So this is a discrete thing. So it ends at the previous sample, and from the next sample we generate the straight line. That is the reason we write this as -2 minus 0.01. Okay, then what do we do? In this interval we want all zeros. So we first calculate the length of this. N1 is length of T1, and then generate H1. So that is, this HT is split into three parts, H1, H2 and H3. So H1 is all zeros. So zeros 1 to N1. Okay. Next we define the second time vector T2, that is now starting from -2, 0.01, same sampling time, and ends on 2. And during this time HT is simply proportional to T, that means in this case T2. So H2 is equal to T2. And finally we need to define this part of the time vector and set all the samples in this to 0. So how do we do that? So T3 is defined like this. Since the last one ended at 2, the next one must start at one sample time later. So this starts at 2 plus 0.01, again sampling time, and goes all the way up to 3. So now what you do? Find the length of this, the number of samples in this, and set all of them to 0. So you have generated your H1, H2 and H3, and all you have to do is to place them one sequence after the other, concatenate them. So you get your H equal to H1 followed by H2 followed by H3, and then you can plot. Subplot I have written here because we are going to plot xt also. This is a part of the entire program, and that program plots ht, it also plots xt, and it also plots convolution. That is why you require subplot 311. But this program segment simply plots ht, and indeed when this program is executed, ht will be plotted like this. Okay, so that is the program segment for ht. Let us now study the program segment for xt. Again, the entire time vector is from -3 to +3. That is already defined in the program. And this can be generated by two unit step functions. One starting with the advanced time of 1 second. Okay, unit step function normally will start from 0, but here it will start from -1 and go all the way up to all the way up to 3. But we want this to come to 0. So what we do is we generate second unit step function and start it at 1 and give it a magnitude of -2. So, and then add the two together, so we'll get a pulse. So let us see. So x1 is equal to 2 unit step d t1. So we use this entire interval, and this essentially what it will generate. This 1 means delay of -1, or in other words advance. So it starts from -1 and goes all the way up to 3, because the same time vector we are using. Then x2 is -2 u step, and now it starts at 1, delay of 1. Remember, for this unit step function with a delay, negative sign was for delayed. So it will start like this. We'll have a -2 value because of the negative sign. And when you add the two, the first portion remains as it is, but after 1, the two will combine to give you 0 here. So note that the generation of xt is slightly different. ht was segment by segment, and then we simply put sequences one after the other. In this case, xt is generated by two shifted unit step functions, appropriate unit step functions, and then adding them. That is what we are doing. So x equal to x1 plus x2, that generates this function, and then you can plot it as usual, grade on. So when you do this, you will get this. So that is your program for calculating and displaying xt. This is a program segment, part of the entire program. Then program segment for the convolution. So it is very straightforward now. So h and x are already available. So you take convolution of h comma x, that is the syntax, and then multiply it by 0.01 in order to get the integrated value, as we have seen. Because the convolution function, let me repeat, that is a sum of the products for a given value of n. So you have to multiply by 0.01 in order to get the integration. Now remember that the convolution function itself has a start point, which is the combination of the addition of the start points of the two functions. So both of them were starting from -3. So our convolution will start from -6, and both functions were ending on 3. So the convolution will go up to 6. So then once this is TC is known, then you can plot y as a function of TC. And if you do that, this is what you get. Note that although we have used a larger time slice, it does not matter, because for the initial part where the functions have not started, the values are 0, so the convolution is also going to be 0. So the real effective part of this convolution is from here, increases like this, increases linearly, then decreases like this, and then is again 0. We shall verify this result in our next session when we perform the calculation for the same functions analytically. Then we will actually obtain the expressions for this as functions of time, and then we can verify the analytic solution versus the numerical solution. This is the result of the numerical solution. So just to see the overall picture, again I have plotted all these three in one frame. So this is your ht, this is your xt. Both of them are plotted from -3 to +3. So the convolution is from -6 to +6. And for your convenience, I'm just giving you the entire program in one screen. So you can just copy it and try to maybe improve it, modify it, and run it. And that's all in this particular session. In the next session, we shall study the calculation of convolution again by analytic method. Why? By suggesting one particular rule which is called as a pair sum rule. So watch out for that session. Right now we end.